Section 13.2 chi-square goodness of fit test, not if fit, of fit test. This one is a new test, to test a hypothesis. And what is this test about? The goodness of fit test, as you can see, it's is an inferential procedure used to determine whether a frequency distribution follows a claimed distribution or not. So it's gonna be slightly different than the other test that we did before. Before we were doing like left tail test, right tail test, two tail test. Here the null hypothesis, as you can see here, is gonna be always H0 to be all the same, H1 different. Different means at least one of the things are different, and I'll explain in a minute what that means. But to do that, let's think about you roll a die once. Is it a fair die? Is that a fair die? Because some dies are not, maybe heavy on the one end than the other end. So in order for that to happen, the probability that you will get each face is 1 out of 6, because there are 6 faces. So to set up the null hypothesis, you would say H0 is the probability P1 for the face 1 equal the probability for phase 2, phase 3, phase 4, phase 5, phase 6 to be 1/6. If you want to set the null hypothesis, you claim that at least one of them is different. So maybe P1 is different than P2. This could be the same as the other ones if you like, but at least one of them is different. So you can write it this way, or you can write like at least one of the PIs is different. Okay, you can write it this way, and that's how we set the null hypothesis and the alternative hypothesis. Within that, what's the idea behind this test? The idea behind it is to compare actual number of observations with expected number of observations if the null hypothesis is true. If the null hypothesis were true. So this means maybe you want to look at data from 2 years or 10 years ago for a certain city or some other example. So when you look at that data, you ask yourself, do you expect the same data to be the same or appear the same this year? Let's say, for example, we can take the number of people on, like if we look on the East Coast, West Coast, Midwest, and then let's say back in 2010, is that number the same? The number of people the same in those regions nowadays? So you're comparing an actual number that you know about back from 2010 to an expected number you expect to be at the end of this year. Is it going to be the same or not? So that's what this test is about. To do so, we introduced two things here. One called observed frequencies. Those are variables because they vary from sample to sample. Now, those are called observed values, and we're going to use capital letter O for that. And then we have expected values or expected frequencies. Those are not variables. They are actually determined by the sample size and the distribution in the null hypothesis. To see how to apply all this, we're going to go through the procedure down here. The first thing, to get the expected values, E over here, we use the sample size times the probability or relative frequency. The probability or relative frequency for each one of them. So you already have, you would have the frequencies. You find from the frequency, relative frequency, or the P's here, the probabilities. And you know the sample size, it will be given. And then you just multiply them one at a time to get the expected values for each one of them. Then after you find the expected values, why do we need to find the expected values? Because the test states that this is the chi-square distribution that we introduced in the previous section. It says the test, to get the test statistic for chi-square is the sum. So if you want to write it in a different way, the sum of the observed values minus the expected values squared divided by the expected values. And when you find the test statistics, you're going to find the chi-square, you're going to find chi-square sub alpha using table 4. Shouldn't be table 4, it's table 7 in this book. Different books, they have different table number. Table 7 in our textbook, which I listed down on this slide down there. So the table 7 with degrees of freedom C minus 1. So how many observations you have minus 1. And then after that, you're going to go through to see, the chi-square looks like this, starts at 0, and then this is the chi-square sub alpha. And then we're going to see this is going to be always on the right side. That's alpha, the area. If the test statistic falls within the shaded region or the rejection region, we reject the null hypothesis. If it falls in here in the dotted region, we do not reject the null hypothesis. Okay, now to be able to use this test, there's some requirements or assumptions. The first thing, that all expected frequencies should be 1 or more. 1 or more. That's a condition we need to check. At most 20% of the expected frequencies, they are less than 5. And as always, simple random sampling. If these conditions are met, then we can use it. We can use this test. And when we use this test, as we did in the previous test, there are two things, either the critical value approach or the p-value approach. And I'll show you an example how you apply both of them. This is table 7. On the right side, as you can see, the degrees of freedom, and we got 5 on the top, 5 columns. Very easy, straightforward to use. So let's look at this example here. In this table, we have 500 people, the sample size. They found back in 2010, the type of violent crime and the expected frequency. So it's given, those are given for us. The murder was expected frequency 6, the next one. So that's a total of 500 if you add them up. Given alpha, level of significance 0.05 or 5%. What I did here, I found the relative frequency for each one of them. Relative frequency, you just take this divided by the total, which is 500. Same thing, 34 divided by 500, next one. And that gives you these decimals. Why we found them? Because we need them to run the testing hypothesis here. So in this table, the observed values that are given to us is 3, 36, and so on and so forth for a sample size of 500. Those are the expected values. To run the test, we need to evaluate the test statistic, this one. And how do we evaluate this? We find first each observed value minus expected. So 3 minus 6, it's negative 3. 36 minus 34, it's 2, and so on and so forth. Then what do? We square each one of them. So the negative 3 is squared to be 9, 2 is going to be 4. This, if you square to get this, you square to get this. Then sum them up. If you add all these up, okay, and divide the total by the expected. So the expected here, if you look, it's 500. So you add all of these up and divide by 500. So you can take out a calculator and then add the numbers up. The 9 plus 4 plus 506.25 plus 462.25. Add them up and then divide this here, keep this the same, 981.5. just keep that in mind for now. The way you do it, these expected values, if some people they put EIs like that, OI, and I is moving from 1 to n depending on the sample size. So the way you do this is you take the difference, or the square of the difference, which is 9, and divide by the expected value. So we have a 9 divided by 6. So to get 9 divided by 6, 1.5. That's where this number came from. 4 divided by 34 is this. 506.25 divided by this, you get this. This divided by this, you get this. And now you add them up. We shouldn't have added them the way I said earlier. We add them up here. That's the right way. So you get 6.529. So you add everything up. This formula that you see here, one thing you need to be careful about, this sigma covers all of them. So I can write down here, rewrite it. So OI minus EI square over EI. I goes from 1 to n. Chi-square statistics. So if you want to write it down, that's like O1 minus E1 square over E1 plus O2 minus E2 square over E2 plus all the way to the last one, On minus En square over En. So table is the easiest way to organize the work. So you always take the observed, expected, find each one's difference, O minus E, then square that, okay, then divide O minus E square by E, and then sum them up, get the sum. That's what we need. That's the chi-square. This is the procedure. Now, when we did this, when we found this, let's keep this on the side. Now we're going to get the critical value chi-square of 0.05 because that's alpha. And it turned out to be 7.815. Where did that come from? The degrees of freedom, if you notice, we have 1, 2, 3, 4. So n is 4. 4 minus 1, 3. So 3 and alpha is this. Let's go to the table. Table 7. Degrees of freedom is 3 and 0.05, this one. So if we go horizontally this way and down this way, that's what we have, 7.815. That's where that came from. So now why we got the critical value? Because now we can draw the figure like so. This is the 7.815. Now we go back to the test statistic. This is the test statistic value. Let's see, where does it fall? Does it fall in the shaded region? No, it falls somewhere here. Chi-square 6.529. So we fail to reject the null hypothesis. We fail to reject H0. Means no sufficient evidence to support the claim, which is H1 or HA, the alternative hypothesis, right? To support the claim. So the claim said, now in 2020, those crime rates will be different. But it turns out that they are going to be the same or almost the same. So we failed to reject the null hypothesis. So at the 5% significant levels, this given data does not provide sufficient evidence to conclude that last year's violence will be different from, or 2010 violence year will be different from this year, or this year will be different than 2010. It depends how you interpret it. So that's for this one. Now that's the critical value approach. How about the p-value approach? P-value approach. In the p-value, we find the p-value and compare it to alpha. If the p-value is less than or equal to alpha, then we reject the null hypothesis. We reject the null hypothesis. Otherwise, we don't reject the null hypothesis. It's exactly the same way as we did in the previous sections. Same exact method. So how do you find this? we first look at the degrees of freedom is 3, right? Degrees of freedom is 3. And we take the critical value that we found earlier, 6.529. The critical value, or the test statistic value. And then table 7, back to table 7. And let's see what we have in table 7. So we look in table 7, I can show you here on the tablet. Degrees of freedom 3. And we would like to see 6.529. This is degree of freedom 3. 6.52, 6.5. So it's somewhere here, right? That's the number, 6.5. So if you project it up, that's between these two values. So between the 0.05 and 0.10. So the p-value falls between 0.05 and 0.10. And remember, alpha was given as 0.05. So notice that the p-value is bigger than alpha. So that's why we failed to reject H0, the null hypothesis. Now, you might say, wait, what happened to these conditions here, or the assumptions? We did not test them. Let's go back and check. It says all expected frequencies are 1 or more. All expected frequencies are 1 or more. So how do you find them out? Well, let's see. Expected frequencies, we found them. 634, 147, 312, right? All of them are bigger than 1. And it says at least 20% of the expected frequencies are less than 5. Okay, at least 20% of the expected frequencies. So what are the expected frequencies here? So at most 20% of the expected frequencies are less than 5 at most. So let's see the expected frequencies. All of them are more than 5. So 634, 147. So these conditions or two assumptions are met. No problem. Another important thing to note here. Let me show you an example from scratch, as this table was given already to us. Very important note to keep in mind. The frequency, when they give us a frequency in a problem, the frequency is the same as the observed values or observed value. So just keep that in mind. That's one thing. And let's say we need to look at another example. Let's say a researcher wishes to test a claim that a distribution of US residents in the United States is different today than it was in 2000. So in 2000, 19% of US population were in the Northeast. 22.9% in the Midwest. 35.6% South. 22.5% in the West. Okay, and based on this, and he collected a sample of 1,500 households in the United States and obtained their frequencies. So here is the region, and these are the frequencies. So for the Northeast, Midwest, South, and West, here he questioned 200 or found 274, 303, 564, 359. They total up to 1,500. So one thing, again, as I said, the frequency is the same as the observed values. These are the O's. And to run the test, Of course, you can go through the claim or the assumptions later on and find out that they are okay, they are satisfied. So we need to find the expected counts. Here we have the observation counts or observed counts. How do we find the expected? Remember, the expected is always you take the sample size times the probability. So in this case, the first one, I'm going to call it E1. E1 is the sample size 1500 times the first one has a probability 19%. So 1500 times 0.19. And if you do so, you get 285. E2 for the second one, 1500 times 35.6%. And 1500 times 0.356. That gives me 343.5. If you get decimals, it's fine. 1500 times the next one. I skipped the second one, the middle one, 22.9%. If you calculate this, this one is not this. This one is for this. 343.5. This is 534. And the last one, E4, is 1500 times the 3 and the percentage, 22.5%. And that gives me 337.5. Okay, so what we've done so far, we got the frequencies or the observed values. We had the observed values. They were 274, 303, 564, 359. And the expected values. The expected values 285, 534, 343.5, 337.5. Then we do O minus E, 274 minus 285, and we'll see what we get for that. We can subtract them. That gives us minus 285, negative 11. And then next we're going to square these. Right? That negative 11 square is 121. And then after that, we're going to divide each number obtained by the expected count or value. So it's 121 divided by 285. So 121 divided by 285. It's about 0.4246. We can go 4 decimal places. And we do the same thing for this one. 303 minus 534. 564 minus 343.5. 359 minus 337.5. That gives negative 231. If you square it, you get 53361. For the next one, we get 220.5. If you square it, you get 48620.25. This is 21.5. When you square it, you get 462.25. And then you do the division. So we look at what we got there when we squared it, divided by the expected value. Actually, you know how I switched the range, the order, this should be switched to. This should be the 534 and this should be 343.5. So we need to fix that out. 343.5, 534, because these numbers look too big to me to be true. So we do 303 minus 343.5, that's negative 40.5, and that would be, if you square it, 1640.25. And if you divide it, you get 4.7751. This is 30 here. If you square this, 900. So the 900 divided by the expected value, 534, that gives us 1.6854. And the next one, 462.25 divided by the expected value, that gives 1.3696. And if you sum them up, then the chi-square 0, or the test statistic, I got 8.255. Now for the critical value approach, critical value, what do we have? We have the degrees of freedom. We have 4 observations minus 1, so 3. And if you use table, not 4, 7, and we need to test the claim at alpha equals 0.05 will be given. You get that the chi-square, the critical value, it's also 7.815. We found that out. Okay, then, and this is the chi-square. If we try to put that in, 7.815, and the test statistic we found was 8.25. So 8 point something here, 8.255. So it falls in the critical region or the rejection region. So we reject the null hypothesis. So it means we have sufficient evidence that the claim H0 or H1, the distribution of the residents in the US will be different. Comparing 2000 to 2020. So overall, if you just like to see the null hypothesis and alternative hypothesis, how you list them out, you can just say that the distribution, you can write it down, it doesn't have to be mathematical formulas. Distribution of residents of the United States is the same today as it was in 2000. And here you just say everything the same, and at the end you say different today from what it was in 2000. Now to get the p-value approach, we know degrees of freedom is again 3, and we have the chi-square, we found 8.255. So now we look in the table and find where is the 8.255 falls in. 8.255, I'm gonna show you here. The same row where the 3 is, 8.25 is somewhere here between 0.025 and 0.05. So the p-value falls between 0.025 and 0.05. Since the p-value is less than alpha, which is given 0.05, we reject the null hypothesis. Means there's sufficient evidence at the level of significance alpha equals 0.05 to support the claim that the distribution of the United States today is different from the distribution in 2000.